Good day everyone. Today I will be explaining my code for solving equations using numerical methods. So here is my code. This is my main and these are my six methods. First one is the bisection. This one performs the bisection method within a single interval to find a root. And then this one return immediately if no root is guaranteed or no sign change. Iteratively narrow the interval until the root is found within tolerance or max iterations reached. Then this one, check if midpoint is a root within tolerance. Decide which half interval to keep based on sign change. This one will save iteration details for display. This one searches for all roots within an interval by dividing it into slices. Applies bisection method on slices where the sign changes occur. If it detects exact roots at interval boundaries within tolerance. It also avoids duplicate roots. Here, here, if a sign change detected in a slice, run bisection to find the root. If no root in this slice, then store info for completeness. Now this is my bisection UI. It's a Simulate UI to display root finding results including summary, step, table, and graph. Moving on to the next one is the graphical method. So in this line of code, it creates evenly spaced x values within the specified range x limit, calculates the function's value of f of x for each x in x vals. And here, it will check each pair of consecutive points to see if there's a sign change, which indicates a root exists between them. It also, if if a sign change is found, approximate the root as the midpoint of the 2 points. If function the value is already very close to zero within the given tolerance, treat it as a root to catch exact zero crossings. Then below this is my UI, and that's for the graphical method. Now moving on to the incremental method. In this code, function that uses incremental search to find the roots of a function. This one, get the start at the end of the search page. This one, list to store detected roots, detailed log of each step, and step counter. In this line of code, it calculates the theoretically maximum number of steps based on a range and step size. Ensure we don't exceed max iter or max iteration. Then this is the main loop, and if there's a sign change, there might be a root between the two values. Approximate root midpoint, then it also avoid duplicate overlapping roots. Then here, it saves the step details in the log. Also move to the next interval, increment iteration counter. Now below these are all my Streamlit UI function that displays the results. Now moving on to the next one, the Newton. In this line of code, functions that applies the Newton-Raphson method starting from an initial guess to record information for each iteration. This one and this one is the starting guess. Then this it compute the f of x and compute the derivative f of x. If the derivative is zero, we can divide, so stop the process or break. And here, compute next guess using the Newton-Raphson formula. And this one approximate relative error in percentage. Log current iteration details. This one, if the error is smaller than the tolerance, stop and return the root within the logs. Update the current guess for the next iteration. Then if max iterations are reached, return the last guess and the logs. Moving on here. This function that searches for roots over range using various initial guesses. List of all detected roots, logs for all guesses. Now here, it is a loop through each initial guess in the specified range with step size. In the record, store all iterations into a big list for UI table. Here is check if this is a new root, not a duplicate of the previous ones. Now these are all my UI. Now moving on to the regular falsi method. This is the function that runs regular falsi on a single bracket only, at next upper. It also computes initial function values at the boundaries of the bracket. Here, to store step-by-step logs used for calculating error in each iterations, store the final roots estimates and iteration counter. And this one is to avoid division by zero, then break the loop. This is the regular falsi formula to estimate the root. Also this one, percentage error, not applicable in the first step. Log iteration details for the UI table. This one, if function value is close to zero or error is small enough, then stop. Then this one, decide which bracket to replace based on sign change. Moving on to the next line of code, function that scans the entire interval in small steps to find all roots using regular falsi. List of all detected roots, all iteration logs for interval for the entire interval. Moving here is to define bracket in each interval step. Here, to check if there's a sign change in the bracket or value is already close to zero. Then also here, if not, it is to avoid duplicate roots. Then also check if it's close to existing roots. Then these are my Streamlit UI. moving on to the final method, the second method. Second method, in this line of code is to find roots starting from x0 and x1. In this one is to store iteration info for analysis or display. Also here, evaluate function at guesses and prevent division by zero. This is the second formula to compute the next root approximation. So here, calculate approximate relative error. This one here is to stop if tolerance met. And this one is to update guesses. Then return last estimated if tolerance is not met. Moving on to the second all roots. This is scan interval with step size, run second on every consecutive pair. Then here, it is to add initial guesses info, add root if new to avoid duplicates. Now below is my Streamlit UI for second method. Now let's try running my program. Let's wait for it. Now here, enter your function in Python syntax, then set the search interval start and end values. Select one root finding method, then click root, run root finder to find roots. Then you can review the result and summary table. Here you can input your function, then start and end. And here you can select methods. Now let's try finding the root of this function. Here's the one. Then click to run root finder. You can see here, these are the table. How about let's change this to negative. Negative, fine. Now let's try another method, incremental method. This one is taking too long because it has so many iterations. Let's pause. Then we have the iterations and the graph. Now for the bisection. Now that's all. That's my numerical methods.